Thank you very much, Xiaogang, and I'm glad you didn't tell the story from last year too much, although everyone seems to know. So thank you very much, and thanks to all the organizers for the invitation again to come to Taiwan. And apologies to Jose, because he's going to give his talk for the second time. We heard it a couple of months ago. So feel free to sleep. So I'm going to be talking about radiative neutrino mass generation. I'm going to talk about models which can do this. I'll briefly mention some flavor physics that Matthias has worked on as well, and some words about searching for this kind of physics at the LHC and indeed existing constraints. So the structure of the talk is I'll first introduce radiative neutrino mass models by kind of unifying them in a sense with the more well-known seesaw models. I'll show you how these things relate to each other. And the relation is going to be through effective operators constructed from standard model fields that violate lepton number by 2 units. Let me say that all these models will be for Majorana neutrino masses, so we're interested in delta L equals 2 operators. And we shall see that the seesaw models arise from opening up one kind of operator. Opening up means deriving it from an underlying renormalizable theory, and radiative models arise from opening up higher mass dimension operators. So the second part will be about these models, a kind of a classification scheme and a construction scheme for these models. I'll then look at a specific new model that we invented. There are many such models. I don't have a favorite model. I'm not sure anyone has a favorite model. There are many such models, and I'll just show you how we analyzed one of them, a new one that we built, and looked in particular at LHC constraints, but also lepton flavor violation constraints. I'll then mention briefly the possible connection between these kinds of models and some flavor anomalies. Our work on that has not yet been finished, so this will be very brief, and then I'll conclude. Okay, so it has been known for some time that standard model effective operators that violate lepton number by 2 units can be constructed, and these can be used to systematically generate models of Majorana neutrinos, okay? Neutrinos which are their own antiparticles. If you just have the standard model field content, so literally minimal standard model, there are no right-handed neutrinos, it's just minimal standard model fermions plus a single Higgs doublet. Explicit in these theories is their theories of just one Higgs doublet. So these things have been classified, and they occur at mass dimension 5, 7, 9, all the odd mass dimensions from 5 upwards. At dimension 5, as you may all know, there's a very famous effective operator called the Weinberg operator. It consists of 2 left-handed lepton doublets and 2 Higgs doublets. It's dimension 5, so it's a non-renormalizable operator. Of course, there are family indices on the leptons, and so there's actually a set of those operators, but they all have that structure. Being dimension 5, of course, you need to put a 1 over m in front of that when you put it in the Lagrangian. And then, as you probably know, if you simply replace the Higgses with their VEVs, and with the 1 over m in front of this operator, you immediately get a Majorana mass for the left-handed neutrino of the form electroweak VEV squared divided by big M, where big M is a scale of new physics that has been integrated out of some underlying renormalizable theory to produce this effective operator. And this is the famous seesaw formula for neutrino masses. It's an explanation for why neutrino masses are so small compared to electrons and other fermions. And it is because we are assuming that the scale of new physics is high, therefore VEV of h over m is a small number, which is multiplied by another VEV of h, and so you get a naturally suppressed set of masses. Okay, so now here's the point. If you take this Weinberg operator and ask how many ways are there to derive it from an underlying renormalizable theory at tree level in a minimal context, then the answer is there are precisely 3 ways to do it. And these are now known as the type 1, 2, and 3 seesaw models. So the point about, now historically, this is not how it happened. Historically, the type 1 and 2 seesaw models were invented kind of at a similar period and kind of independently by several people. And the type 3 seesaw model was invented by our chair here, Zhao Gan, and other people in Melbourne quite a number of years later, something like 15 years later. So why was this third possibility missed? And the reason it was missed is that people were just randomly inventing theories. Well, not randomly, but they weren't thinking through all the possible ways of writing down a seesaw theory. They found a good way, the type 1 seesaw. They found the second good way, the type 2 seesaw. And then they kind of forgot to look for others, or they didn't ask the question, are there any others? So the nice thing about approaching it in this way, asking the question, how many different ways are there to derive this effective operator from a renormalizable theory, is that if you do that, you won't miss any theories. Okay? So I think that's a good way to think about the origin of these three different seesaw mechanisms. Now, if you then look at the higher dimensional delta L equals 2 operators, mass dimension 7 and upwards, all of those guys, apart from one example, which is a simple generalization of the Weinberg operator where you multiply by h dagger h to the power of n. Apart from those ones, which are generalizations of this guy, all these other operators contain other fields, which are not neutrinos or neutral Higgses in the external lines. They're quarks or charged leptons or whatever. And therefore, if you want to take that delta L equals 2 operator and turn it into something that generates a Majorana neutrino mass, you've got to do something with those external lines. So you've got to close them off in loops, basically. And therefore, when you're looking at the UV completions of dimension 7 and up, delta L equals 2 operators as the engine rooms for Majorana neutrino mass generation, you're necessarily talking about radiated mons. So what you see here through this argumentation, which is kind of well known, is that the well-known seesaw models are at one end of a spectrum, right? Opening up dimension 5 operators in a minimal way, and then when you look at all of the other operators, you get all of these different kinds of radiated neutrino mass models, and there are many of them. So you can see we have a whole family of candidate neutrino mass theories that at least have a kind of a systematic structure behind them. There's a way to construct all these theories in a systematic way from this perspective. Okay. So let me give you a historical example. This is something called the Z-Babu model. So again, it wasn't constructed this way, but you can think of it, reinterpret it like this. There's a certain effective operator. There's a classification scheme where this is actually given a name. Its name is O9. It contains 4 lepton doublets and 2 right-handed charged leptons. So this is a delta L equals 2 gauge invariant effective operator. If you just had this effective operator, you would have this sort of contact interaction in your effective field theory. And then you ask, well, how can I open this operator up? And one way to do it is like this. You introduce 2 different scalar particles. One couples to 2 lepton doublets, and the other couples to 2 right-handed charged leptons. And it turns out they have the quantum numbers such that they also have a cubic term in the Higgs potential between those scalars. So this is now opening up that operator. If you then want to turn it into a self-energy diagram that gives you a Majorana neutrino mass, this is what you have to do. All right. So you have to add a couple of standard Higgs-Yukawa interactions, replace the Higgses with their BEVs, and then join the dots in terms of forming loops and so on. So these scalars here, H and K, are interesting because these are exotic particles beyond the standard model of particle physics, and they can be searched for in experiments such as the LHC, and they can be constrained in their parameter space from the same experiments. This guy here is a doubly charged scalar, and this has been a target, a search target of the LHC. Okay, so this is the deal. You start off with some effective operator, you open it up, you get some exotics, you then ask, what are the constraints on the interactions of these exotics and the masses of those exotics, and what else can we do with these theories? So let me show you some bounds on this charge 2 scalar. These are old bounds from run 1 LHC data, and the bounds depend on what branching ratio assumptions you make for the decays of the doubly charged scalar. This search was not done just in the context of the Z-Babu model. It was a general search for doubly charged scalars, also in the context of the left-right symmetric model. That's why you see doubly charged scalars with indices of L and R. So, but anyway, it's also implicitly a search for a Z-Babu type of doubly charged scalar. And the bound that you get depends on the branching ratios for the decays. But anyway, it's somewhere in the range of 350 to 400 JeV from run 1, lower bound on the mass. Atlas also provide, these are Atlas bounds. Atlas also provided a kind of table that allows you to interpolate between different branching ratio assumptions for these scalars. The Z-Babu one is analogous to the right-handed doubly charged scalar in left-right symmetric models. Okay, so this is the kind of information, the kind of bounds you got from run 1. What about run 2? Well, there is a paper by Atlas which generalizes, which repeats this analysis for at least some run 2 data. And what you see, so this is now run 2, 13 TeV. What you see is that the bound has now increased from about 320 JeV to 450 JeV for one of the particular cases that they consider, which is where the doubly charged scalar decays 100% of the time into like sign electrons. Okay, so you can see that what going to 13 TeV has done, it's allowed you to increase the bound make the bound more severe by about 30%. Okay. I now want to sort of make a small sort of digression, but it's relevant. It's a comment on naturalness in type 1 seesaw models, and it perhaps provides a motivation for considering a broader class of theories beyond the type 1 seesaw. See, type 1 seesaw, of course, is everyone's favorite neutrino mass model. It's a terribly obvious model. If you stare at the minimal standard model Lagrangian and you ask yourself, what am I going to add to it to give neutrino masses? The first thing you would think of is this. You just throw in 3 right-handed neutrinos. I mean, it makes the spectrum nicely quark-lepton symmetric. You then recognize that the right-handed neutrinos are gauge singlets, so you can give them Majorana masses, and you should, because that's a renormalizable gauge invariant term. So you should just write it in the Lagrangian, and then you have your type 1 seesaw model. So it's a terribly obvious theory to write down. It may well be correct, but it's very, very difficult to test experimentally because the new physics in the theory is typically at a very high scale. If you want to have the seesaw mechanism operating in its full glory, you need the right-handed Majorana masses to be really large, and also these things are gauge singlets. So you've got very massive gauge singlets that you're trying to look for, and that's essentially hopeless. So it would be interesting if there was some reason to consider different kinds of theories that may appear less elegant, but at least are more testable. Now here's an argument about a problem in at least the vanilla kind of type 1 seesaw, and it starts with a paper by Visani in 1998. So whenever you introduce a new high mass scale in some standard model extension, you have to worry about destabilization of the electroweak scale, the naturalness problem. And you indeed can draw a self-energy graph involving the right-handed neutrinos in the type 1 seesaw model, which will eventually destabilize the electroweak scale if the Majorana masses are large enough. This is what Visani computed a long time ago, and this is the correction that you get to the mu squared parameter in the Higgs potential. It depends on the mass of these right-handed Majorana neutrinos, and if you impose a naturalness bound where this should be less than 1/10 squared, that gives you an upper bound on the scale of the new physics, as you would expect from a naturalness argument, and numerically it's a few times 10 to the 7 GeV. Now, that's an interesting bound. That's an interesting bound because of thermal leptogenesis. So again, the favorite model for many people of baryogenesis, of explaining the matter-antimatter asymmetry of the universe, is thermal leptogenesis in the type 1 seesaw model, the mechanism that Fukugita and Yanagida invented some time ago. Now, that only works if the masses of these right-handed neutrinos are sufficiently large. And the lower bound is actually, it depends on whether you're doing flavored or unflavored leptogenesis, but the lower bound is comfortably higher than this upper bound from naturalness. It's about 5 by 10 to the 8 GeV. If these heavy neutral fermions, these right-handed neutrinos, are any lighter than that, then that implies that in order to derive the light neutrino masses, you need to use smaller and smaller Yukawa couplings as you make this mass smaller and smaller and smaller. And that means you're naturally suppressing the CP violating effects that you need in leptogenesis. So that's why you get a lower bound on the masses of these guys. This was computed by Davidson, Ibarra, and Giudice et al. So there's a kind of a tension here between naturalness of the type 1 seesaw mechanism without supersymmetry or anything like that. Of course, if you supersymmetrize this, then this bound goes away. Nevertheless, in the vanilla model, there is this tension. We asked the question in our paper, is this true in general? If you do a full 3-flavor analysis, which Visani didn't, and if you considered all possible kinds of leptogenesis, not just from the decay of the lightest right-handed neutrino, but the second lightest, or maybe even the heaviest, and so you can generalize the Visani formula. Here it is, written in the most useful way down here. So this is a bound on each of the mass eigenstates. Here is the Visani number, and here is the correction due to 3-flavor effects. These are the masses of the neutrinos, and this is an unknown matrix called the Casas-Ibarra matrix, and you have to scan over those parameters in examining those bounds. And we were wondering if there was any room to have successful thermal leptogenesis of some sort, hierarchical thermal leptogenesis without violating naturalness, and the answer was no. Whatever you did, however you wiggled around in the parameter space, you always got upper bounds that were comfortably below the lower bound that you need for leptogenesis. Even for N3 leptogenesis, which is a rather exotic thing, that depends on the mass of the lightest of the neutrinos, and you can look at that and say, well, the lightest of the neutrinos could be massless, and therefore this bound could in fact be infinity. But as you make M-min lighter and lighter and lighter, what happens is that N3 decouples completely. That's why there's no naturalness bound when M-min goes smaller and smaller and smaller, and because it decouples, it's not going to be of any use to you for nucleus and for baryogenesis anyway. So there's no way out of it. So there seems to be a tension in non-supersymmetric type 1 seesaw between naturalness and successful hierarchical thermal leptogenesis. So it provides some encouragement for considering alternative theories. The alternative theories don't have to be radiated neutrino mass models, although they could be. Another simple alternative which we looked at was to simply introduce a second Higgs doublet that greatly increases the kinds of parameters that you have in the Yukawa sector, and it turns out when you look at all the details, which I won't go through here, there is a region of parameter space which obeys both the naturalness constraints as well as the Davidson-Ibarra type of bounds. So there are many ways to get around that observation. All right, so now let me return to the main topic and now look at models that you get by opening up the D equals 7 operators. So remember, the D equals 5 operators, when opened up in a minimal way at tree level, give you type 1, 2, and 3 seesaw mechanisms. What about dimension 7, the next most complicated case? First of all, let me note that the classification of these operators was done by Babu and Learn some time ago, was re-examined by Dugubeyer and Jenkins some time later, and also a group around Walter Winter in Germany has been working on such papers, on such issues in recent times. Some of you in the audience have seen this slide before a few times. This is a kind of a list of the effective operators. Here are the dimension 7 ones. There are 4 different ones from the point of view of their flavor content. Actually, this number 2 here means there are 2 different versions of this, depending on how you contract the indices to make it gauge invariant. There are two versions of that. But there are only a handful, of mass dimension 7 operators. They all have 4 fermion fields in them, and also a Higgs doublet. This number here is the scale of the new physics that is incorporated in the coefficient of this effective operator, if you assume that all of the coupling constants involved in forming that effective operator from the fundamental theory are of order 1. So this is a worst case scenario for the scale of new physics. If you have coupling constants that are not 1 but might be 0.1, and you multiply a few of them together when you derive your neutrino mass, you will bring this scale down, and you can bring it down into the LHC regime fairly easily. Right, you don't need many small parameters to bring that down into the LHC region. And this also, I won't expect you to read all of this, but this just tells you that which of these effective operators or models derived from them, at least implicitly, have received some attention in the literature and which have not. So there are many operators that have yet to be properly analyzed in the literature, and so there are many radiated neutrino mass models that actually have yet to be constructed. So what we did was go back and have a thorough look at the dimension 7 operators and complete the job of writing down all of these models. That has been done partially over the years mainly by Babu and co-workers, and also Tony Z's original model is based on this operator. Here are some examples of dimension 9 operators. There are many of them, and all right, some of them have actually formed the basis of some models. All right, so in this paper from a year or 2 ago, we constructed all the minimal models that you can derive from these mass dimension 7 operators. By minimal, we mean the following. We are going to introduce 2 kinds of exotics. Exotic scalars, massive exotic scalars, and massive exotic fermions. These fermions are either vector-like fermions or Majorana fermions, so they just have a bare mass. So we can make them as massive as we wish. So here are the effective operators. And now you can go through a sort of a topological exercise where you look at all the different ways that you can open these operators up. This operator here, by the way, you'll recognize is just a generalization of the Weinberg operator. There's the Weinberg operator, sorry, LLHH is the Weinberg operator, and here is H dagger H, which simply just multiplies that by a gauge singlet. Okay, so you can now go through this exercise. There are different topologies. One of them is where the exotic particles are entirely scalars. So remember the Z-Babu model had 2 exotics which were purely scalars. This table summarizes the different kinds of models you have in terms of their particle content. Here is the operator, and here are the quantum numbers of the scalars that you need to introduce to open up the operator. And this is a complete list. And you can see that some of these scalars have already featured in some specific models. There are also, another topology is a scalar plus fermion extension. There are quite a number of these. These are all Dirac fermions, vector-like Dirac fermions, and here are some scalars. And the new theory that I will look at in some detail in a moment and set collider bounds on and lepton flavor violation bounds on is this particular theory, which is a new one that we chose sort of at random, just to give an example of how you do this kind of analysis. And finally, this is a case that holds just for this generalization of the Weinberg operator. Okay, so you can go through that exercise, and it's not too difficult. But now, for each particular model, to do a thorough analysis of each particular model, to look at all the constraints and look at all the search strategies, that's a little bit of work. And you kind of have to do that on a case-by-case basis. So let me have a look at one particular model. It has a scalar and a vector-like fermion. it comes from opening up this particular effective operator. The constraints I'm going to look at are just from run 1. That's all we had at the time we wrote our paper, and we haven't updated it to run 2. I wish I could give you the new bounds, but I can't. So this scalar is a leptoquark. If you have a look at, here is the Lagrangian involving the exotic fermions and scalar, and you can see that phi is a leptoquark scalar, okay? And it has various couplings. This particular coupling we're just going to put to 0 because actually it plays no role in neutrino mass generation. So just for simplicity, we're just going to set all of those to 0. Of course, eventually you would not expect that these would be exactly 0. But there's a large parameter space here to explore, and we have to make some simplifying assumptions, otherwise we kind of go crazy. All right, so those will go to 0. Also, it turns out with this particular particle content, there are renormalizable gauge invariant terms you can write down that violate baryon conservation. We're simply going to forbid those by imposing baryon conservation because we don't want to, otherwise, if you just did phenomenology, of course, you would get very severe constraints on the coefficients of these things. All right, so here's the neutrino mass generation diagram. It's a one-loop diagram. Here is the exotic fermion in mass insertion approximation. Here is the leptoquark scalar. You also need a couple of Higgs bevs. If you look at the formula by evaluating this loop graph for the neutrino masses, you see it's dominated, it's proportional to the down quark masses. Of course, the B quark mass is the largest of those. So we're going to suppose that the other parameters involved in this diagram are not arranged in such a way as to prevent the B quark from dominating this physics. So we're going to have B quark dominance. And again, for simplicity, to explore the parameter space, we're going to switch off mixing with the first and second generation quarks. So with those simplifying assumptions, this is the formula for the neutrino, Majorana neutrino mass matrix for the left-handed neutrinos. That involves these Yukawa couplings of the leptoquark to a lepton and a quark, and the leptoquark to a lepton, and the exotic fermion. Now, I didn't comment on the quantum numbers of the fermion, but you see its hypercharge is rather exotic. So one of the entries in that in this doublet, it's an electroweak doublet with respect to like quark. One of them has got electric charge minus a third, and that mixes with the B quark. So this B prime mixes with the B quark. And then the other member of that doublet is a rather exotic thing. It's a minus 4/3 exotic quark. So we're going to get two sort of B-like mass eigenstates from the mixing of the B prime with the standard B quark. Also, at this level of approximation, one of the quarks is massless and two are massive, which is fine to fit the neutrino oscillation data. This is not a fundamental feature of the theory, it's a feature of the simplifying assumptions we've made about the parameter space we're willing to explore. Okay, I just want to introduce a parameter, zeta, which will play some role in the phenomenology. This is just a way of parameterizing the effective 3x3 Majorana mass matrix for left-handed neutrinos. And there's an unknown Casa-Ibarra-like parameter that occurs in that, which we'll call zeta. All right, so now let me just run through the bounds. So you can search for this vector-like capital B quark, the guy that mixes with the normal B. It's been searched for by CMS in these modes. And when you look at the branching ratio of B to BZ in our particular theory, then the CMS bound translates into a lower bound on this fermion of 620 JeV just from run 1 data. From run 2 data, the bound will now be more severe. You can search for the leptoquark explicitly. You can try to produce the leptoquark, so it will be pair produced both by gluon-gluon fusion and QQ-bar annihilation. And then when it decays, it will have two decay modes into a lepton doublet and a top. Sorry, into a lepton and a top, or a B and a charged lepton and a top, or a B and a neutrino. Okay, and when you look at the branching ratios for these decays, an interesting thing is that the same parameters that determine the neutrino mass are also the parameters that come into the branching ratios for these decays. So there's an imprint on the way these exotic leptoquark scalars decay that is imparted there from the need to fit the neutrino mass matrix. So, and that puts some constraints on what the branching ratios can be. And therefore, if we were ever lucky enough to find such a thing at the LHC, its branching